All right. Good morning, everyone. Sorry for the bit of delay. We were doing some little technical difficulties there this Monday morning. I want to say good morning and welcome all of you to the September California, Nevada Drought Early Warning System Drought and Climate Outlook webinar. Thank you for those that have joined us previously and those that might be joining us for the first time. My name is Amanda Sheffield, and I am the Regional Drought Information Coordinator for NIDIS in California, Nevada, affiliated with the Cooperative Institute for Research and Environmental Sciences at CU Boulder. This webinar is co-hosted by the California Nevada Adaptation Program, a NOAA CAP team. We've designed these webinar series to provide the region with timely information on current drought status and associated impacts, as well as a preview of developing climatic events. Before we get started, please note that this webinar is being recorded, and the recording will be available on drought.gov and our YouTube channel later this week. Very quickly, for those that may not be familiar for NIDIS, let me introduce us. Our mission is to improve the nation's capacity to proactively manage drought-related risk by providing those affected with the best available information and resources to assess their potential for drought and better prepare for, mitigate, and respond to the effects of drought. We do this through several drought early warning systems, as you can see on the map here, where we disseminate information as well as work with our new and existing networks of federal, tribal, state, local, and academic partners to make climate and drought science accessible and useful for decision makers. Many of the activities in our drought early warning systems fall under these different categories, including observation monitoring, plan and preparedness activities, prediction and forecasting, interdisciplinary research and applications, as well as webinars like this and communication and outreach. I did quickly want to mention, if you're interested, just grab the QR code. We are doing a special pilot where we do take information such as you have in this webinar, but take it a step further by providing tailored sector-specific information on a monthly basis. We've been doing this in particular for three sectors. And if you really are in Southern California or invested in public health, agriculture, or water utilities and want to be involved, please reach out to me at my email, or you can go to the QR code and find some more information on the website. And we welcome new attendees to that one. And it's taking sort of the information we have in this webinar, but going a step further to provide the Outlook information for some of those sectors. And just quickly, if you're not on our email list or you want to be, you can sign up at the QR code there. You can also always go to drought.gov, news and events. You can find past webinars, the latest news, sign up for our emails. I did want to mention there's quite a few stories that might be interesting to you guys that we just put out this recently. If you're interested in the Mississippi River, we do have a new dashboard there. I know it's a little bit of a different region, but we do have stories on ENSO, Western drought, and over the summer and early fall, we've been updating the drought and wildfire maps. And one last thing before we get started, I wanted to mention that the Nevada State Climate Office and the National Weather Service are doing a fall recruitment drive for COCORAS, which is the Community Collaborative Rain, Hail, and Snow Network. Basically, it's a volunteer network of backyard weather observers. The website's there at the bottom, but basically, they use this information is used, the precipitation measurements you'll be taking are used by agencies to accurately look at that information. They go to the Weather Service, others and beyond there. And really the only equipment you need is a standard 4-inch diameter rain gauge and access to the internet to enter reports. You can do them daily or whenever they're available. And volunteers are really needed all across Nevada. You can see the map there. Every dot is an example of someone who's reporting. And you can see there's not a lot in Nevada, and they especially need a lot more observers, and especially those in rural and higher elevation areas. So I just wanted to mention that if you are in California or any other state, you do also have COCORAS, and I'm sure they would gladly welcome volunteers for those as well. But I did want to specifically mention that Nevada would love to have you as well. All right, with that, we'll go ahead and get started on our speakers. Our first speaker is Julie Kalansky. She is from CNAP, and she's going to be giving the drought and climate update and outlook. And Julie, I'll pass the screen over to Julie. Sorry about that. One second. There we go. Julie, we can see your screen, but we can't quite hear you yet. Do you want to unmute your... Julie, we still can't hear you. Does anyone else, any of the other speakers, do you hear Julie? Not just me?
No, I'm not hearing any audio from Julie either.
Julie, do you want to?
Can you hear me now?
Yes, now we can.
Okay. Are you seeing the right set of slides? Somehow I got muted on
the screen just disappeared. So the screen, you're still a presenter, but like when you started to come onto mic, we lost your slides.
Are you still, can you see them now or no?
No.
Okay, I'm sorry for the technical difficulties.
Let me like share it back and maybe send it back to you.
Well, let me try resharing. I think I accidentally stopped sharing.
There we go. We can see your your screen just not presenter yet. There you go.
Okay, and you're seeing the right display, not presenter mode?
Yes, the correct display, and we can hear you, so I think you're good to go.
Awesome. We're there. We made it. Okay, well, great. Sorry about all that. I'm going to provide both the look back and current conditions and also a quick look forward for California and Nevada. And so here I'm starting with the drought status, and what you can see here, and I was actually going to do a time series, but these stat tables do an excellent job. You can see right now that about 40% of California is in drought, which is similar to what it's been throughout much of the summer. But if you look at the start of the water year, it was only a little bit less than 11%. So there has been quite this increase since the start of the water year and how much of California is in drought. And as you'll notice, it's in the southern 2/3 of the state. Similarly, in Nevada, there has been a significant increase since the start of the water year, which was 32% is in drought, and now it's 65%. And we've actually seen that drought increase over summer, over these last 3 months. And there is almost 10% of Nevada that is in extreme drought. So there is, while both California and Nevada have seen an increase in drought since the start of the water year, there's significantly more drought throughout Nevada and more extreme drought as well compared to the two. So how did we get here? This is just looking at precipitation patterns, a percent of normal. This is from the start of the water year through the end of August. And we've heard probably a lot about this, but the dipole this year, where the northern part of California and the very northwest corner of Nevada was above normal precipitation. And then beyond that, the southern portions of both states were drier than normal, and that the intensity of the dryness increased moving south. I wanted to look at it over the summer months since the last time we've had a webinar, and you can see the summer there's been areas that have been particularly wet. So this is since the last 3 months, since June 23rd. And then in particular, this last week, you can see that it's showing that it's extremely wet. But as we know, this time of year, generally there's not a lot of precipitation in the summer, and so that percentage can be a little bit misleading. So oops, wrong way. So I showed the anomaly, and so the anomaly for the region is actually relatively small. It's between less than 1/3 of an inch in some areas, or between about 1/3 and an inch in those areas that are showing anomalously wet. I was kind of curious to look at to see, well, what does this mean for soil moisture? So this is one location. This is in the Santa Ana watershed. It's a little hard to see this map, but this location right here, so more coastal California. And this is soil moisture at various different depths. You can see but really what I want to focus on is the 5 centimeters, so that top layer, that wetted up during the winter months, and then a bit in May too. There was a break in the record. But what you can see here is some of these late season events that we have. It's not really getting down to the deeper soil moisture, but at least the surface moisture is responding. And so that top 5 centimeters, you're starting to receive a response in the soil moisture. Looking at temperature patterns, and so this is since the start of the water year, October 1st. And on the left, and this will be true for the next one, you're looking at daily maximum temperature. And throughout much of Nevada, temperatures were, 2 to 3 degrees above normal throughout much of the state. California is a bit more varied, where you have areas that were below normal. The last 1991 to 2020 mean, whereas the minimum daily temperatures, so the nighttime temperatures, were actually much warmer and generally throughout both of the states. And so like we did for precipitation, was looking at that for the last 90 days, so kind of as a proxy for the summer months, more or less. And you can see actually minimum daily temperatures for much of California and the southern part of Nevada were cooler than a 30-year average, but parts kind of in the northern part were a bit warmer and more the Central Valley. Similar to the water year as a whole, those minimum daily temperatures were warmer than those maximum daily temperatures. So next I was looking at the evaporative demand, and this is the way to think about this is the thirst of the atmosphere, so how much the atmosphere dries up the landscape. And this is regardless of vegetation type or anything, it's just looking at the atmospheric variables of temperature, humidity, solar radiation, and wind. And you can see this is a 12 months, so 12 months from September 17th. The areas in the drought map where we see more drought are the areas with higher evaporative demand, with some exceptions along the coast, and in some extreme in much of kind of southern to central Nevada, pretty extreme evaporative demand over the last 12 months. Looking at the 3 months, so kind of as again similar proxy for the summer, the strongest evaporative demand was along the central coast in California, while other areas still had high evaporative demand in kind of the southern half along the diagonal in Nevada. And this, especially during those summer months, it can be an indicator for fire risk, so how dry the fuels are. And we'll get to a little bit more talking about fires, but the fine fuels in Nevada this year and this summer were significantly dry, and that was part of what contributed to the fire risk in the region. I will say most recently, this is looking at just the 1 week with all the moisture that we've had in the atmosphere, and in some places actually receiving some precipitation. You see that wetness category is showing up throughout much of Nevada and in the eastern part of California. So this is just a look at, so what does this mean from stream flow and reservoir storage? And this is looking from the California-Nevada River Forecast Center, and you might have to squint a little bit to find your favorite stream flows, but this is what % of normal for a handful of sites that California-Nevada River Forecast Center monitors and provides results for what of the total year-to-date stream flow. And you kind of see that north-south divide that we saw in precipitation, which makes sense that the streams are responding similarly in terms of the % of normal, where in the northern part of California in particular, you see higher values. Reservoir storage is a little bit more complicated. So this is, again, looking at a handful of various different reservoirs throughout California and Nevada. Many are still above normal, or with some being below. This being kind of the first year of drought for some places, oftentimes reservoirs have about 2 years. And so we haven't seen as much of an impact to the reservoirs as we had, say, compared to stream flow in some of those places that had less precipitation. So, and you can, for example, Lake Tahoe is at 183%. Shasta, which is up here and a little bit harder to see between all the dots. Oops, sorry, over here is at 107%, and Pine Flat's at Pine Flat down here is at 70%. So looking at the 2020 fire season to date, this is from CAL FIRE, and each of these little gray flames represent a fire that has been put out, whereas it's hard to see with the layering of it, but you see a couple of ongoing fires. So year to date, there's been almost 7,000 wildfires, and these colors in purple are the 5-year average. So more wildfires than the average, but if you look at the acres burned have been less than average. And so And then looking at, for Nevada, it's part of the Great Basin Coordination Center, and so through this area. But for the whole GAC, there are 21 new fires as of last night and 11 ongoing fires, and these green lines show the fire perimeters. So now looking ahead briefly, this is just looking at the fire potential, and this is showing one day, I think it's on the 23rd, where you're seeing that in Northern California, there's moderate risk in significant fire potential, whereas in Southern California and much of Nevada, there's little to no risk. This having to do with the moisture that's forecasted, which we'll get to in a second. And then this shows, through time for this Northern California GAC region, what is that significant fire potential? And I will say for the Southern California, Nevada, while not shown, this green remains throughout these 7 days. Another question is, well, why is this? And this is looking at 2 different models of 7-day precipitation total forecast. And you can see that they vary a bit. So the color scale is you see inches here on the left. And so those green colors are between, ½ inch and 1/8 of an inch. So we're not talking about necessarily a lot of precipitation, but for this time of year, it is. And you can see some of that moisture coming up and, getting wetting in some areas. And then the European model actually showing potentially more significant rainfall throughout Central California. And I think part of this is just the scatteredness of it. It can be hard to forecast, but just understanding, what the potential is for the next 7 days. Now looking to a little bit longer lead times, here's looking at temperature. This is from NOAA's Climate Prediction Center, and this is 8 to 14 days, and you see it's leaning pretty likely above normal temperatures for much of the region. And then this is a much longer lookout, that's 3 to 4 weeks. Similarly, a 50 to 60% chance leaning to above normal temperatures for much of California, and 40 to 50% chance down to 33 to 40% chance for parts of Nevada. Looking towards that 8 to 14 day precipitation outlook, much of Nevada is showing 33 to 40% chance of above normal, whereas similarly for Northern and Southern California. But the 3 to 4 week precipitation outlook it's very difficult to forecast at this time, but isn't really leaning one way or another. And lastly, I'll wrap up with, before the summary, is looking at right now for the El Niño Southern Oscillation Outlook. It's a La Niña watch. And so this is from NOAA as well, the Climate Prediction Center. And it's looking at whether it will be La Niña or neutral. And you can see by October, for October, November, and December, the probability increases to almost 70, just above 70%, and it starts to drop off as we get later in the season. So with that, I'll wrap up with some summary comments that during water year 2025, drought grew both in California and Nevada. It went from just under 11% to almost 40% in California, and from 23% to almost a little over 65% in Nevada. There was this north-south precipitation gradient, though throughout most of Nevada was below normal. Many of the reservoirs are near normal, even though the stream flow showed that similar north-south dipole. Fire potential is repressed due to more moisture, especially over the next 7 days. And then 2 to 4 weeks slightly above normal temperatures, but precipitation forecast is less certain, and currently we're in a La Niña watch. So I will stop there. And Amanda, I can send it maybe back to you.
Great. I'm going to take the screen over so Dan can present next, but there is a quick question. Is there a way to determine how much above normal temperature? They have IOWs a lot hotter than normal, or just a little?
For the CPC?
I'm guessing that's what I think. I think it's about the outlooks potentially, and I can answer.
So
Go
Yeah,
ahead.
if you want to go ahead, go for it. I was going to say for the 8 to 14 day, there are actual forecasts for temperatures. So I don't know off the top of my head that I can look at. I would say 3 to 4 weeks, given the extended lead time, it's pretty hard to know for certain. And so I think that likelihood range is probably the best way to think about it.
Yeah, I think in the longer term, especially as you get further out, you don't have actual values. We just is how much it may be hot. It will be hotter or less than normal or things like that. You don't know the actual values sometimes in some of the forecasts that are further out. So okay, with that, then we'll speed on, keep on going, and we'll pass over to Dan Cayan, who is with CNAP, but also at the Scripps Institution of Oceanography, to talk about Sacramento and Upper Colorado River hydroclimate similarities and contrasts. Some of his research.
Thanks, Amanda. Can you hear me?
Yes, we can. So you're good to go.
Terrific. Hi, everybody. So this is work that's been developing by a number of us over probably a couple generations. But in any case, thanks to NITIS as well as CNAP for support, in addition to other federal and state sponsors. This first slide is showing the record of precipitation for the, I take that back. This is actually discharge in the Sacramento and Upper Colorado River naturalized. And what one is struck by the smoothing is the degree of coherence, at least at times, across these two somewhat distant western watersheds. Amanda, if you could go to the next one. Here they are, shown in red. This is an annual precipitation map over CONUS and beyond. Interestingly, the Upper Colorado is 4 times the area of the Sacramento Basin, but the Sacramento discharge is almost twice what is generated in the Colorado Basin, reflecting the aridity in the Colorado region there, and of course the at least occasional wetness in the Sacramento Basin. The Colorado River provides just about 10% of the developed water supply in non-environmental water supply in California. Sacramento, more than a third. So that gives you a little bit of the scale of the importance. They're both important, of course, and particularly to different users. But in any case, this is statewide numbers. I should also note that the Colorado, of course, does provide water to Nevada. I think there's part of the group here is Nevada. I think 300,000 acre feet goes to Nevada. So it's also an important source there. Amanda, please, next. This is the annual cycle of precipitation month by month for the Sacramento and the Colorado drainage from U.S. climate divisional data. And of course, you're struck by the Mediterranean signature in the Sacramento Basin. About 80% of the precipitation on average occurs between November and March, and not so in the Colorado. much more evenly distributed across the year. The atmospheric thirst, which is shown there at the top right inset, which Julie had mentioned, of course, is much more dictated by the annual cycle of temperature and related measures, and very similar in both basins, although a bit delayed in the Sacramento compared to the Colorado Basin. Let's go to the next. So if one looks at a simple way of determining the contribution seasonally of precipitation to the respective basin's discharge, not surprisingly, the Sacramento Basin is really dominated by core winter months precipitation. These are correlations across the 4 seasons: autumn, winter, spring, and summer. And almost 75% of the, well, say half of the variance is determined by DJF precipitation in the Sacramento Basin. More like a quarter of the variance is determined by DJF in the Colorado Basin, and a bit more in the Colorado Basin in springtime, March, April, May. So you can see the disparity here in the two basins as far as their precip contributions. Let's go to the next one. So this is a composite of dry years on the left and wet years on the right of monthly precipitation anomalies for Sacramento drainage at the top and the upper Colorado at the bottom. The beginning of the either dry year left, wet year right, water years is delineated by that vertical red line. And what you're struck by is, of course, the peakiness in the deficit in the Sacramento Basin, essentially those important cool season months, whereas the Colorado Basin anomalies, so right now I'm looking at the dry case on the left, are really spread throughout a broader annual profile of dryness. Again, this is a composite of a score of dry years there at the left and wet years on the right. The other thing that strikes is the fact that dryness, even when you focus on individual rather intense dry years, is actually preceded by dryness in the year leading up, and to some extent persists during the following year. Wetness has some of that, but perhaps not quite as strikingly. The other thing that calls out here is the fact that the magnitude of anomalies of precipitation in the two basins is quite vastly different, where the Sacramento Basin precipitation anomalies are just larger, which kind of scales like the amount of precipitation in average that the two receive. Let's go to the next. So if one looks at the signature of low flows in the Colorado Basin, which is mapped out there at the top, where we took stream gauge information across the nation and anomalized it and looked at the magnitude of anomalies during Colorado low flow years. This is somewhat dated. This was a paper that was produced in the early 2000s, but I think the pattern is probably accurate, where you can see dryness in the Colorado is really accompanied by dryness across from most of California and on into the Midwestern states. The dryness indicated by the unfilled dots, which are scaled to represent the size of the flow discharge anomalies there. The other thing that stands out when you look at the relationship of Sacramento and Colorado annual water year precipitation, the contingency diagram that's shown there on the left upper, is the fact that there is a coherence between the two, where dry events tend to be associated with across the two watersheds, as well as wet. About 1 of every 6 years in a record of more than 120 years from the divisional data are dry in both basins. If that was a randomly occurring set of samples, you'd expect 1 out of 9. And interestingly, wetness co-occurring is about 1 of every 5. So there's a pretty statistically tight relationship. Of course, it's not perfect. What I did there at the bottom left is I composited the mid-level atmospheric circulation for water years during years where both Colorado and Sacramento were dry. And you can see by the yellow-green colors the relatively high geopotential height, high pressure, if you like, extending well across the mid-latitudinal Pacific Basin, a signature of the storm track, essentially receding to the north. And of course, you can see poleward low pressure, low geopotential height anomalies there. Interestingly, the correlation plot on the upper right shows how when the Colorado is in its dry state, the Columbia in the Pacific Northwest tends to be in the opposite wet state. Let's go to the next one, Amanda.
And then you have about 4 minutes left.
Okay, I'll sprint. So the other thing that you're struck by when you look at the interannual precipitation records across the two basins are these runs. And to my eye, I'm really struck by the dry runs, which are the brown bars here, which represent below median water year precipitation. Let's go to the next one, Amanda. Getting to the runoff efficiency, the ratio of runoff to precipitation. Of course, in the West, where lots of the West is really dominated by low runoff efficiency because of aridity and atmospheric thirst. This plot owes to Greg McCabe and Dave Woolak. and they show the play out across the West. The Colorado Basin much more deprived than the Sacramento Basin, as shown there by the numbers. Let's go to the next, which makes the point that during dry years, the runoff efficiency becomes even leaner by almost a factor of 2 less in the Colorado and a little more in the Sacramento Basin. Next one, Amanda, please. One of the important elements as far as Western precipitation are atmospheric rivers. Let's go to the next one. And of course, more so along the coast, California, if you parse the precipitation volume that attributes to just the upper 5% of heaviest daily events, it really dominates the interannual variability. This is a figure that Mike Dettinger produced years ago. Let's go to the next one. And John Rutz has shown how atmospheric rivers penetrate into the West from the West Coast. And you can see there in the center map the proportion of total annual precipitation that one can attribute to ARs. Getting into Colorado, of course, not nearly as much as California, which partly explains the degree of volatility that we have in California, but also the more bountiful intensity. Let's go to the next one. This is a map that Mike put together, kind of showing the same story where you can see the variance explained by ARs really comes to a high point in the state of, still non-negligible in Colorado. Let's go to the next. Of course, we're in a really impressive period in climatic history where everything is warming very decidedly and will likely continue. So these are projections of warming that Dave Pierce put together for the state of California several years ago. The story's very similar in the latest generation of projections. Next one, Amanda. Which shows these are actually observations where precipitation is plotted vertically and temperature horizontally. The years of the 2000s are called out on each of these plots. This is the Colorado, which is the one that's featured. Sacramento is in the lower inset. But what you're struck by is the descent of our water year climate towards warming, and in many cases warming and drying in the last couple of decades. Let's go to the next one, Amanda. This is true of both basins. Looking forward, a study that Dan McAvoy authored that looked, this is ETO across the parts of the West. Sorry, Colorado is neglected here, but the story is similar. And we can expect by end of 21st century an increase of as little as 5%, but as much as more than 20% of atmospheric take of the available water, if it is available at the land surface. I think that may be the last one, Amanda, if you go to the next slide. So thank you, and back to Amanda and colleagues.
Great, thanks, Dan. If anyone has questions, just keep popping them into the question box and we can answer them there or answer them in email afterwards. Forrest, I'm going to pass it over to you. Forrest will be presenting on OpenET as well as its new tool called Farms, which is a new tool for farmers and ranchers they've built into OpenET. And Forrest, we can see, but we can't hear you yet. Oh.
There we go. All right, I thought I hit the button. I did not. There we go. How about now?
We can hear you and we can see the presentation, so you should be good to go.
Great, thanks. So thank you so much for the invitation. And yes, happy to talk a bit about a tool we launched earlier this year, the Farm and Ranch Management Support Data Interface. This is an interface to the OpenET data that was designed around requirements developed in close partnership with farmers and ranchers across the US, but it is also a way to access data in reproducible ways for medium-sized regions. And I'll talk about briefly some of the other data services and tools for folks looking at retrieving larger data. Just as quick background and context for folks that have not heard about OpenET before, OpenET was developed because in many of the gap analyses and informational needs assessments that were conducted by the NASA Water Resources Program and the NASA Western Water Applications Office, field scale evapotranspiration data came up again and again as one of the top priority needs for water resource managers and agricultural producers, particularly in the Western US. And of course, it intersects with everything from irrigation management to groundwater management programs, to assessment of drought impacts and quantification of vegetation water stress and associated wildland and fire risks. So over the last about 7 years now, we've been working to develop a fully automated system for mapping evapotranspiration from satellite data at field scales at that spatial resolution of 30 to 100 meters. The OpenET data is available at a spatial resolution of 30 by 30 meters, or a little less than 1/4 of an acre per pixel. Currently, across the 23 westernmost states in the US, we are preparing to release data for CONUS, so we'll have the full CONUS coverage here by the end of the year. For the Western US, data is available at daily, monthly, and annual timescales, extending back in the public data catalog to 1999, and we're also working to release data from 1985 to present to capture that full 40-year time series of data. It's heavily driven by the Landsat series of satellites, presently 8 and 9, which gives us an observation every 8 days, and then historically from Landsat 5 and 7. Some of the individual models also incorporate data from GOES, from the MODIS instrument on Terra and Aqua, from SUMI NPP, and we're working on integrating data from EcoStress and Sentinel-2 as well. And then more information about the OpenET project in the background is available there at openetdata.org. In addition to the field scale, or the data at the original field scale satellite resolution of 30 meters by 30 meters, we have also pre-computed summaries for about 4 million agricultural fields in the 17 westernmost states in the US, and we'll be working on expanding this coverage as well for states like California, Nevada, as well as Oregon, Washington, and Idaho and Utah that have their own state-run boundary mapping programs. These data sets are excellent, and the field boundaries are really useful and generally accurate. Quick note that OpenET has been a community-driven effort from the beginning that's taken an open science approach. So these are some of the team members here, 3 federal agencies, a number of universities working with private sector partners, and about 2.5 years ago created the OpenET nonprofit, OpenET Inc., to help coordinate activities and try to develop strategies to ensure long-term support for the OpenET system and operations, working with state, federal, and philanthropic partners. I want to note that there are 6 modeling teams that are involved in OpenET. These were teams that were interested in making data open source, that had been working towards operational use of satellite-driven ET data, either with state or federal agencies in the Western US. So that's the team involved. In addition to this ET data from the 6 individual models. We also produce an ensemble ET value computed as the mean of the ensemble after flagging and removing outliers. An important part of the OpenET project has been not only advancing the science and developing the data sets, but also finding ways to make them available through a co-development user-driven approach. So the first thing we released was the Data Explorer, which, as the name suggests, was to allow anyone with an internet connection and a web browser to easily access and explore data without any additional required expertise or specialized software tools. So that's available there at explore.etdata.org, a point-and-click interface that lets folks retrieve data for any location of interest. To facilitate retrieval of data at scale and integration with other applications, we developed the OpenET application programming interface. So for those of you that are interested in bulk retrievals for larger areas, that's the best way to access data and retrieve it, including integration of OpenET data with other applications that folks may be developing related to drought or farm scale water management. Really good documentation, also some nice YouTube videos there on getting started with the API. I'll skip that today. I'll also note that the monthly data is available as an open data collection, publicly available in the Google Earth Engine data catalog, and we're working to add the scene assets and scripts that would allow folks to compute daily data at scale as well on Earth Engine. The code for 5 of the 6 models is available as open source software, and then I'll talk today about FARMS. And so FARMS was developed to provide a user-friendly graphical user interface to the API, recognizing that farmers and ranchers use a lot of technology, but frequently don't have a programmer on staff and aren't well, that's changing, especially for the younger generation. Number of folks are comfortable in Python, but this was developed to make it easy for folks to define boundaries, save them, store them, and then create reproducible queries to retrieve data for regions of interest of up to about 150,000 acres. So I'll talk about that in just a moment. Wanted to quickly mention that OpenET, we have now over 11,500 users. Data is being integrated into state water data information systems in 10 states at either regional to statewide scales. Applications related to groundwater management, monitoring and reporting of water use, different watershed management, forest management applications, incentive-based water conservation programs, and then on-farm irrigation management and scheduling applications. We have conducted an accuracy assessment. I'll just, in the interest of time, briefly refer you to John Volk's paper in Nature Water that was published last year. Included 148 flux tower sites, 70 in agricultural land cover types, and we selected those sites from about 350 total and filtered to ensure that the daily average energy balance closure was at least 0.75 during the growing season and 0.6 during the non-growing season. As a result, we ended up with a mean average daily energy balance closure of 0.88 during the growing season. So a really good, strong subset of flux towers were used in this analysis. And then for the ensemble ET value for croplands, I'll let you quickly skim this and pick your favorite accuracy statistic. We looked at multiple different statistics across different time periods, and all of these met or exceeded the user requirements for accuracy for these different time scales for a range of applications. The one that's kind of pushing it is the daily accuracy, especially for on-farm water management and irrigation scheduling. We're working right now to reduce the mean absolute error and root mean square error. However, the bias error is still good. So I think for applications that are really trying to ensure that root zone soil moisture remains well above maximum allowable depletion, the bias error is really the important thing, as long as there's not a consistent underestimation of ET and consumptive use. It can still be used, and we see actually about 40% of the retrievals from the OpenET API right now are reported by the users for the purpose of irrigation scheduling. Again, all that said, that's a key focus for us, is reducing the MAE and RMSE at those daily time steps. So I'm going to quickly run through how to access farms. If you have not used OpenET before, the first thing to do is to visit https://account.etdata.org. You will need to sign up if you'd like to use farms. A Google account is helpful because we need some place to store the reports that is secure and only accessible to the user. If you use a non-Gmail account, we can also store them in a cloud archive for you as well. But you'll need to sign up. When you do sign up, just asking for some information. This is just to help us ensure if someone is hitting the system heavily, we want to make sure that it's for an intended use and not just an error in a script. Again, with 11,500 users currently and growing by a couple hundred users per week, we are just trying to make sure that everyone is playing nice in the sandbox together, and we're able to deliver data to all users while managing the compute resources available to us as efficiently as possible as an open science effort that's trying to maximize the availability of free data. At the bottom, you'll notice a cloud project ID and access code. If you have a cloud project ID and you have an Earth Engine account that's linked to a cloud project ID, please do enter that. That's very helpful, just ensuring that some of the data calls to the API on farms are going through the user's Earth Engine account as opposed to our limited queue, and that will just help us, again, maximize the availability of data for as many users as possible. So if you have a cloud project ID, enter that. If not, you can leave that blank, and don't worry about the access code field for now. So I'll move on to farms. So this was released earlier this year, again, as an interface to make it as easy as possible to automatically retrieve data, create recurring reports. You'll notice at the top that you can add new boundaries, view reports, view boundaries, and then there's a really helpful help menu. And to start by adding new boundaries, that's typically the first step. There's a couple of ways to do that. You can upload shapes. So as a shapefile or a GeoJSON, you can draw your own, or you can select from our existing. I'll start by walking you through the upload shape functionality. The area limit here is about 500,000 acres with a total of 500 features. That's not strict. That's recommended just based on really to avoid timeouts for the report generation calls and the API calls that are behind farms. So this is really a limit of what we can do with the queue we have available to us through Earth Engine. If you have really simple polygons, you can probably increase the feature limit. If they're really complicated or complex, it's probably a bit below 500. So the number of vertices matters as much as the total number of features being uploaded. And then you can also, just to make sure that the shapefile and GeoJSON are compatible, there aren't sort of overlapping boundaries or polygons that aren't closed, you can also use MapShaper there to quickly sanity check the shapefile before you upload it. So when you upload that, you can just drag or drop into that interface. It's going to display some of the properties back to you. An important one is going to be the fields found in the shapefile. We do need the user to select the unique identifier that they would like applied to the reports. So whichever field in the shapefile has the unique IDs that you would like linked to the outputs from OpenET, we do need the user to select that field from the shapefile. Once that's done, you can send it to map, send it to the maps. You can also in there in the attributes select additional attributes that you want to pull out of the shapefile and have included with any report from farms. Once that's done, the first thing it'll do is display the boundaries back to you, back to the user, just so you can verify and make sure, yep, that's in the right place. It overlaps with the region I'm interested in. And again, this can be agricultural fields, it can be wetlands, it can be burn scars. This will work. This can be large parks in urban areas. This will work anywhere in the Western US and soon CONUS. If those look right, you can say save shapes as data sets right there as a data set in the lower right. Quickly mention drawing your own boundaries. There is this, when you click on that button, there are the menu that pops up on the right, so you can easily select center pivots. You can use the custom polygon tool to select subsets of a field or to outline irregular fields. There's also a rectangular square if you have plots or nice square fields. That's also available there. And then once they're drawn, you can edit them if needed. And you can also come back to these, the shapefile data sets and edit them. And then you can also move them if needed and delete boundary elements. So pretty standard online GIS type functionality and tools. Again, once you're done defining the regions of interest, you can save them as a shapefile data set. And then finally, there's that option to select from existing boundaries, again, for states like California, Nevada, Oregon, Utah, Washington, that manage their own field boundary mapping programs. These are a great resource and usually, but not always, excellent. So you can do the same thing. You can come in and select a subset of fields. It works better if they're nearby. If you're sort of picking fields all over the West, it's usually better to put those into separate, or all over California, all over Nevada, better to put them into separate shapefile data sets. But you can also select from the existing boundaries. Again, once you've selected your region of interest, just click that Save Selected. Once those are done, you can click the View Boundaries tab. That'll bring up all of the fields, the shapefile data sets you created in your account. You can download them if you've drawn your own. And you're working with a landowner, a really nice thing you can do is actually download that shapefile and share it with them. And that's also something that can be edited. So that's a really nice piece of functionality if you're working with any landowners that don't already have shapefiles for their farms and ranches or other areas of interest. Once you've selected the field boundary data set of interest, you can select associated reports and view them. You can also delete the boundaries if you're done with them. If you've run a report and there was something wrong with the request or it failed, it will come back and you'll get this error that says there are 0 rasters which meet the request criteria. Please do check the help file if you get that message, or you can reach out to support@etdata.org. And then here's an example of what a successful report would look like. And you can also create new reports for a set of boundaries. When you do that, we'll ask you to choose the shapefile you want to work with, name the report, select the interval, daily or monthly, select the start and end date, select the models and variables you would like to have included in the report. So here's an example of selecting all 6 models in the ensemble and multiple variables, the ET, the fraction of reference ET, the normalized difference vegetation index, and the precipitation. Those are all variables that are available. When you click Run, that's going to take some time. And so that's being added to the queue with all 11,000 plus users. It can take anywhere between 5 to 15 minutes typically, sometimes up to an hour if there's a user that submitted a large request ahead of you in the queue. But once that's done, the report will display back to you, both with a map on the right that allows you to select any fields. It will plot those on the left so you can compare fields within a given year. We're working on tools that would allow you to compare the same field for different years as well, which we know for drought impact assessment would be really important. And then on the left, you can select the fields to display there. So you can select the model and the variable. And then there's also functionality here that will let you download all data generated by the report. So you can download that as a CSV or a GeoJSON. You can configure report settings. You can also, see, to the left of that download data, you can also send the report to a PDF if you wanted to print it out and take it out to share with a landowner in the field in a place where you had limited cellular connectivity. And then lastly, you can configure some report settings. So you do have the option. The reports are all secure and only available to the users, but you have the option of sharing the report. So you can copy the URL. You can make the report public. You can also password protect it or archive it. I know that was a lot to cover, so I just want to quickly say if you have questions about the functionality or you have any issues, support@openetdata.org is currently the most reliable way to get a response. Some of the individual team members were starting to get a little bit swamped, so support@openetdata.org is the best way to get a response. You can also email me with suggestions. We certainly recognize that for drought monitoring and management applications, having not just the absolute values, but the monthly anomalies and weekly anomalies would be valuable. At the moment, we're in the middle of updating the OpenET Collection 2.0 data and preparing to release Collection 2.1. Once that's available, we expect it to be stable the collections to be stable for at least the next 12 months. And we will allocate some time and effort to producing those anomalies from a 30-year monthly and weekly means as well, or 8-day and monthly means if we can. So that's on our to-do list to produce additional derived drought metrics related to things like the evaporative stress index and other ET anomaly maps. Thank you. I know I've run just a minute or two long, but happy to answer questions via email or stay on for 5 minutes and answer questions via the chat. thanks so much. And again, thank you to Amanda for the invitation and chance to chat with you today. Appreciate it.
Great. Thanks, Forrest. I don't see any questions at this time. I'm going to go ahead and put the final screen up, but I'll let people enter questions. Or as you said, either him or I, an email, or any of the speakers will try to get your questions answered as we can. I'll give people some time for us to enter some questions, but I just want to thank everyone for joining us today, and thank you to our great presenters. I apologize for some of the technical difficulties that slowed us down a little bit and kept us away from some of the content, but I'll mention again that the recording of this webinar will be available on drought.gov and the NICE YouTube channel later this week. Our next webinar is scheduled for November 17th. I will note that we may be switching platforms. So right now we use GoToWebinar. We may be switching to a different platform because of restrictions and a few other things. So be on the lookout for our listserv and our emails to sign up for the next webinar, but it is scheduled for Monday, November 17th. As I said, if you have any questions or any comments, feel free to reach out to me. If you would like to join the Southern California pilot as well, feel free to reach out to me as well. With that, I don't see any questions, but don't hesitate to reach out, and I'll go ahead and end the webinar and say, hope you have a great week.